Alright, welcome to Metaphysics with Jesse. So we'll be talking about physics problems, but also the meta is for the metacognitive things that you should be doing, both during and after you're doing a physics problem. So today we'll be focusing on what should we do after we finish a problem. This can also happen during a problem, but it will usually happen at the end. So the problem we're going to be looking at today is a projectile motion type problem with a twist at the end. So it'll start off with just some initial velocity at some angle, and we want to find the range. Later on in the problem, we'll be adding a collision at the peak of the trajectory, but for now we just have projectile motion. So again, let's draw a little copy of this up here. So we have some initial velocity v naught at an angle theta, and we want to find r, the range. So this will be a typical projectile motion problem. So I'm going to write down the position as a function of time first. So in the x direction, we have to choose our origin. So I'm going to choose the bottom left point as x equals 0, y equals 0. So the red spot. So we have 0 initial position. We have an initial velocity. And that will be v naught cosine theta. So that is the adjacent component. So that's linear in time, and we have no acceleration in the x direction. So no acceleration term. Similarly, in the y direction, we have we start at y equals 0. We do have initial y velocity, v naught sine theta. And in the y direction, we do have an acceleration of minus g. So that term will be minus gt squared over 2. We can also write down the y velocity and x velocity. So vx is a function of time. So we could take the derivative of this top equation. Derivative of the 0 terms are just 0. We have this linear term in time. So we notice that the velocity is constant in the x direction. So it's just v naught cosine theta, which is the initial velocity, which makes sense since we have no acceleration, so there's no change in velocity. Vy is a function of time, so we have a similar sort of thing happen with the v naught sine theta term. But it kind of, as we expect, our y velocity is positive for a while, but then it goes negative. So if I take the derivative of this term, I get minus gt. I want to figure out what the range is, so I want to figure out where it hits the ground over here. So the way we figure that out is say, how do we define this point as opposed to some other point along this trajectory? There are a couple of ways to do it, but I think the easiest one is to say this point is special because y equals 0. So I want to find the point, call it t naught. So I want to find y at some time, some unknown time, and I want y to be equal to 0. So I can take this y equation and set it equal to 0. With one change. So this is no longer any time. So any time t, the variable, describes this whole trajectory, t naught describes just this final point. So let's plug in t naught here also. Okay, so now I can solve for time. So it'll tell me the time when I get here, and then I can use that to find the distance in the x direction. So the time is going to be equal to 2 v naught sine theta over g. And then we can plug this back into the quantity that we're interested in. So the x position at this time t0 is what I'm calling the range, or capital R. And so if I plug that back in, I get 2 v naught squared cos theta sine theta over g. So you might recognize this as the range equation. Sometimes they combine this into something that I believe looks like sine of 2 theta, but I'm not super interested in manipulating this expression to look simple. But a couple things to notice: so the units work out. Velocity squared over an acceleration is a distance. These pieces are unitless. So this is kind of the result we're looking for. So now the question is, and the question we'll think about at the end, is what happens in this modified problem. So we have the same sort of setup. We launch a projectile. So let's say this was the distance we just found, r. But we have a couple changes. One, there's this object up here. Call it capital M. So we're going to have a completely inelastic collision with that object. So it's going to stick. They're going to stick together and fall together. And so the question is, how do they fall? Do they fall on some shorter trajectory? Do they fall on some longer trajectory? Do they fall straight down? And what can we predict? So the thing we're gonna come back to at the end is it's hard to make predictions, but we can at least think about it in two different regimes. And so little m will be the mass of our projectile. So the first thing is, what if the mass of this object is much larger than the mass of our projectile? So it'd be like if we launched a ping pong ball at a giant bowling ball that was floating in the air, and they stuck together and then they fell. Well, we wouldn't expect them to go very far after they collided. So we would expect in this case that the new distance, so I'll label this new distance d, so we don't know which one of these it is yet. So in this case, if m is much bigger than little m, so this thing's going to fly up, hit it, they'll stick together. But because little m was so small, they'll just fall straight down. So in this case, I expect the new distance to be r over 2. And the other case is, what if little m is much bigger than big M? So big and little don't necessarily mean which one's bigger or little, they're just keeping track of which one's which. So in this case, if my initial projectile, so what if I launch a bowling ball and it collides with a ping pong ball in the air? Well, in this case, I don't think the bowling ball is going to care very much. So if the projectile is very heavy and if this thing is very light, then the bowling ball basically just won't notice that it's gone on a different path, and so it should get its original length. D should go back to R, so it should land where it would have landed if there was no ping pong ball in the air to collide with. But these are just predictions, kind of based on intuition. So now let's actually work through this problem. So we set this up in kind of a similar sort of way. I'm going to break the problem into kind of 3 different parts. Let's keep this blue for now. So I have the initial, the first part of it, call that 1. I have the collision, it'll be part 2. And then they fall together, so that'll be part 3. So let's do the first part. Well, if we launch a projectile at the same v0 that we had before and at the same theta, the same angle, until there's a collision, this projectile doesn't see anything different. So that should look exactly the same. But it only makes it kind of halfway to its destination, and because the first half and the last half are symmetric, we can use that to say, well, the position up here before the collision, well, it should happen at half the time we found before, so t0 over 2, and it should be half of the original range. So originally it was 2 v0 squared sine theta cos theta over g, and now it'll just be 1 v naught squared sine theta cos theta over g. The other thing I need to know is y at this point. So what is that going to be? So I can go back in and plug in the t0 expression that I got before into y, and so that'll give me two terms. The first term will be a v naught squared sine theta squared over g, and then the acceleration term will give me 1/2 g t squared, so v naught squared sine theta squared over g squared. So I can cancel those g's. So these terms look similar, just this is half of the first term. So I'm going to get v naught squared sine theta squared over 2. The other things I need to know are what is Vx at this point. So I'm going to do a collision problem. So I need to know Vx and also Vy before the collision. So Vx we found was constant, so that is easy. It's the same velocity that the object was moving in the whole time in the x direction. For Vy, we've picked a special point to have this collision happen, and that is right at the very top of its trajectory. So right before the collision, this object had positive y velocity the whole time, and right after the collision, it'll fall back down. So at the very peak, we've chosen the peak so that, or the definition of the peak is when Vy equals 0. So that if Vy is 0, then it's not traveling in the y direction. So it has 0 velocity. So we'll use these things now to do a collision problem. So initially in my collision, or before the collision, I have two objects. They both carry momentum individually. And my collision is really only happening in the x direction. So before I have my little mass and my big mass, and they're gonna run into each other, or little m and big M. I don't necessarily care which one actually has more mass. And then after, I just have some bigger object with V final. And so this one is gonna run into it with V initial. Okay, so let's write that out. So initially, this is the initial half of the equation. My small m mass has momentum m v naught cos theta. My large m mass has 0 momentum because it has zero velocity. This one hanging up in the air is not moving before it gets run into. You could think of it as just like a floating bird or something. And finally, they're stuck together. This is the final half of the equation. They're stuck together, so their masses have combined, and they have some final velocity Vf. I can solve for that velocity since I know everything else in this equation, and it's going to be V naught cos theta, so the initial velocity of the little m mass times a factor little m over little m plus big M. So this thing here will always be less than 1, so if I run into something that's stationary, I'll always have to slow down a little bit. Okay, so now we can do the last part of our problem, which is part 3. And if you remember, part 3 is taking the collision and letting it fall to the ground. So our objects have already traveled partway to this thing, and now they're going to travel kind of the second half of their trip. Let's restart the problem kind of at this point. So this collision happens, let's say our new t equals 0. And we're going to go back and write down the same things we wrote earlier. So we want to write down x of t, y of t for this new problem, this new second half of the problem. So now at t equals 0, we do have an initial x position. So x equal, we're going to leave the origin at the same place it was before. So over here on the left, we have the first half of the problem that we're ignoring now, and we just are working on the second half. But our exposition starts kind of halfway in between at the value we had earlier. So that was v naught squared sine theta cos theta over g. So that's our initial exposition. And we still have a x velocity, but now it's the combined velocity, or vf, that we just found. V naught cos theta little m over little m plus big M times time, and still no acceleration in the x direction. In the y direction, we found that the y component of position was v naught squared sine theta squared over g. And this is still accelerating downwards, so it's still 1/2 or minus 1/2 gt squared. We can write down vx as a function of time, vx as a function of time. So the derivative of the constant term is 0. The derivative of the linear term in t is a constant. So the x velocity is still constant, but it is now a different constant. It's been multiplied by this factor. Vy, so I guess I forgot one term here, which was the initial y velocity, but that was 0 since we were at the peak. So the derivative of this to get velocity is 0. The derivative of this piece is just going to be minus gt. And so now what do we want? We want to know the x-coordinate when we hit the bottom here. So how do I define this point? Well, this point is defined when y equals 0, when y is a function of t equals 0. So let's set this up. So I want to find at t final, I know y equals 0, but I have this expression for y, v naught squared sine squared theta over g minus 1/2 g t final squared. So if this is equal to 0, t final is going to be v naught sine theta over g, and x at t final is going to be this expression. When I plug that in, v naught squared sine theta cos theta g, or sorry, cos theta over g. And then I have the term that goes linear in t. If I plug in t final, that looks like v naught squared sine theta cos theta over g times little m over little m plus big M. Okay, so now, so this is this thing that I'm calling d, the final distance. So this is the end of the problem. We have some answer. All of these things are known. I was given v naught. I was given theta. G is a constant that I'm always given. I know little m and big M, so I know this d. And so I've technically finished the problem. What I want to do now is think about how this problem relates to the earlier problem where we just had projectile motion and I solved for r. So I want to compare d and r and think about what we got. So it's always possible, or it's not always possible, but in many problems it's possible to rewrite an expression in a slightly different form. So I'm going to do a little bit of work v naught and rewrite d. very suggestive way. Okay, so if you go back and look at this expression down here, I have just factored out a v naught squared sine theta cosine theta over g from this term, or sorry, 2 times that. So I get 1/2 from this term, and little m over little m plus big M over 2 from this term. So this was the first term, this was the term with little m over little m plus big M. And so if I look at this piece, and I go way back and look at my result for R, which was here. So R was 2 v naught squared sine theta cosine theta over little g, or over g. And see, this is the same thing. So that's convenient. So I can rewrite D. D is R. So this collision problem looks like the collision-free problem. It's supposed to be little m. So times like 1/2 plus something. So the first half of the collision problem looks exactly like the collision-free problem. So we go half the distance to R from there. The second half has this m dependence, so we can think about what that means. And remember, there were 2 things that we wanted to think about. One is big M is much bigger than little m. So if the thing hanging in the air is very heavy, we said it's just going to fall straight down after they collide, so it should be R over 2. So that was the prediction we made. So big D equals R over 2 if big M is much greater than little m. So does that actually pan out? So let's say big M is much greater. So if we look at this term, this denominator becomes very close to just big M. So if little m is very small, we can ignore it. And then we have little m divided by big M. That thing will be very much less than 1 if big M is much bigger than little m. So if this term is much less than 1, this whole thing will be much smaller than 1/2, and so we can ignore it compared to this 1/2. And so we do get, in fact, that D is roughly R over 2. So the other case was the reverse. What if our projectile is very heavy and it collided with something very light, like a ping pong ball or a fly in the air? Does it actually care? So let's do that case now. So now little m is very large and big M is very small. So this denominator goes the other way. We can ignore this m and just focus on our little m in the denominator. So now we have little m over little m plus some small factor that we're ignoring. So that becomes 1, or approximately 1. So this whole term becomes 1/2 because of that 2. So now we have 1/2 plus 1/2, that's 1. So D becomes approximately R. So after we finished the problem, there's a couple things we did. So we got this answer. This answer isn't too bad. It's not like a super neat answer, but I think there's always comparison that can be done to other simpler problems. So in this case, if we compare it to the just projectile motion problem with no collision, we can kind of see that we can rewrite our new solution in terms of the old solution plus some kind of correction factor. And that's a really useful trick in general to use. And we can also double check that our predictions, kind of our intuitive predictions, actually do pan out from the algebra. And if we take these limits with the 2 masses, we do actually get the answer that we expect, which is a good check for our own intuition. But it wouldn't be. We always want to actually go through the work and check what we're doing. All right. Thanks for watching this video, and I'll hopefully be posting more. I hope to get into questions from quantum mechanics and E&M and maybe some Lagrangian mechanics, but I really like this problem from intro mechanics, so I thought I'd start here.